Inverse and combined variation. So we've already talked about direct variation last time and finding that constant of variation or that rate. The inverse variation is when two things are inversely related. So not directly related. In other words, one goes up, the other one goes up, one goes down, the other one goes down. These are inversely related. So that means if one goes up, the other goes down, and vice versa. Okay, and vice versa. To set up your inverse variation problems, we set these ones up a little bit differently. So we still need to establish the two pieces of data, or what it is we're talking about. So establish the two kinds of data. Again, are we talking about apples and oranges? Are we talking about cars and tires? Whatever. Figure out what your two kinds of data are. And then instead of arranging them like all the apples as the numerator or all the money as the denominator, you arrange them as diagonals. And the reason you need them to be diagonal is because as one is going up, the other one is going down. They need to be on opposite sides of the fraction bar from each other. So arrange as a diagonal one set. And then the other set is your other diagonal. Again, we'll do a couple of these. It'll make sense. And then we solve. And we still solve by cross multiplying. That part hasn't changed. So we're still going to cross multiply. All right. So 5 machines takes 12 days to complete a job. How do you know that that's an inverse variation problem? Well, let's think about this. The more machines you get, the shorter or the lower the number of days it should be to complete a job. Okay, so this is something that if I had more machines working, it would take me less days. So as I increase the number of machines, I decrease the number of days. That's an inverse variation. You have to read that and kind of think that process through. Remember, you're going to set that up as a diagonal because they're inversely related. So you're going to do 5 machines takes 12 days. Okay, diagonally set that up, inversely related. Okay, and then your other diagonal is going to be how long will it take for 8 machines to do the job. Okay, so that's how you're going to set that up. And then we're going to work on figuring it out. How long is it going to take 8 machines to do this? So we'll put our x over here, and we'll cross multiply. 8x equals 5 times 12, or 60. 8x equals 60, and x is then going to equal 7.5 days. So the more machines we had, the less number of days it took. Okay? So you can see how that works. Let's scroll the page up and do a second example just to make sure we are understanding this. Okay, example 2. A 10 diameter gear is in mesh with a 5-inch diameter gear. If the larger gear has a speed, so the larger gear is the 10 diameter gear. That one has a speed of 25 RPM. How many RPM does the smaller gear turn? So think about this, a really large gear and a little tiny gear. So if this guy is spinning, right, and this one's spinning, one's going to be spinning faster than the other. So I'm going to do 10 and 25, that's my diagonal, right? And then 5 inches, and I don't know how fast that's going to be. So this is going to be inches, and this is RPM. Okay, so we, again, don't forget that the 10 and the 25 have to be diagonally from each other. So we're going to cross multiply. We're going to get 5x equals 250, and then we're going to divide by 5, and x is going to be 50. So let's think about this. 50 RPM. The big one turns a certain number of RPMs, 25, and the little one turns 50. Makes sense that the little one's turning much faster than the big one. Okay? So 50 RPM is what we get for our answer there. Good? Inverse variation using a constant of variation. This is no different than what we've been doing anyway, right? We're going to inversely relate the two pieces of information, and we're going to just go ahead and solve the problems using the inverse variation. So I'm going to ask you to just kind of skip this piece for now, and we're just going to jump right into the problems because they're almost identical to what we just did right here. So let's go ahead and clear the screen and scroll. So we're going to look at these examples. A landscaper needs 5 people to complete a commercial job that takes 30 hours. Again, more people should take less hours, so we know that this is an inverse. Make note of that. That's the first thing you should look at and see. Is this a direct variation, more people, more hours, or is it inverse, more people, less hours? So how many hours will it take to complete the project for the following number of workers? So this is our rate. So we're going to do people and hours. So I'm going to do 5 people takes 30 hours. Again, because it's inversely related, those are set up diagonally from each other. That's really important. How long will it take for 3 workers? Cross multiply. 3x equals 150. And then we're going to go ahead and divide by 3. And we're going to get 50. Okay, so 50 hours. Less people. Only 3 people, so obviously it's going to take more hours for them to complete that job. Okay, well, what if they decide, if it normally takes 5 people, 30 hours to do the job, what happens if we decide to get more people? 8x, cross multiply again, that 5, 30, that was our given inverse. We know that's the rate. More people this time, right? So divide by 8, and x equals, we're going to get 18.75. So it's going to take us less hours if we have more people. Make sense? And the last piece is the combined variation piece, and this part gets a little crazy. Combined means that we're related in a couple of different ways. Related both directly and indirectly. And that makes it a little bit challenging as far as writing the equations directly and indirectly. So I want you to think about how we're going to solve these combined variation problems. They're very similar to how we were solving the joint variation problems. So we're going to write the equation using our keywords. Okay, write the equation using keywords. We are going to find K using that first half of the equation, or first half of the information, and then we are going to solve the problem using K and the second half of the info. Okay, kind of crazy. Let's try a few. Some things you need to know. So there are clues in the sentence that you're reading that's going to tell you how to set up your equation. So the clues are this. If it says directly, I'm going to write it over here. If it says they're directly related, we're talking multiplication. If it says inversely related, we're talking division. Okay? So, and don't forget that varies directly is your K part, right? Multiplication using K. All right, so let's do this. Z varies directly. That's what I've read so far. Z varies directly as the square of x. So as the square of x, that means that I have to multiply by the square of x, or x squared. As means multiply. Okay? And inversely as y. Inversely means divide it. So I'm going to divide by y. So that says z varies directly as the square of x and inversely as y. Now, I'm going to write it again over here, the same equation. Why am I writing that equation over again? Because remember, we have to use the first equation we write down to figure out what k is, and then we use the second equation to actually solve the problem. So let's read the first part. Find z when x is 8 and y is 15. X is 8, y is 15. And the constant is 12. So lucky for us, this is an example of when you know the constant. So we have it this time. We can just jump right into solving if we already know what it is. So find z when the k, the constant, is 12. X is 8, so plug 8 in. We're going to square that 8, and then divide by y is 15. Okay, so we're going to go ahead and multiply that all out. So that is 12. 8 squared is 64. And divide it by 15. So 12 times 64 divided by 15 is 51.2. So we didn't need the second equation when we know what the constant of variation is. Okay? So we don't need that one when we know. When we don't know, then we do need to write the equation twice. So let's try this. It's not going to give me much room to work because I can't get rid of this. Well, maybe I can. Hang on one second. See if I can get rid of this. Okay. So, number of hours it takes P persons to assemble M machines varies directly as the number of machines and inversely as the number of people. Okay? So, directly as the number of machines, okay, and inversely as the number of people. So directly as the number of machines, and inversely, because we're dividing, is the number of people, and that's the number of hours. The number of hours it takes P persons to assemble these machines varies directly as the number of machines, so multiply K and M, and inversely means divide by P. So there are my two equations. Let's see if we can figure this out now, because remember, we have two tidbits of information. 3 people can assemble 10 machines in 5 hours. 3 people, 10 machines, 5 hours. So 5 hours, 3 people, 10 machines. What are we missing? We don't know what k is, so we're going to use this and solve for k. I'm going to multiply both sides of my equation by 3 to cancel. And I get 15 equals k times 10. And then I'm going to divide by 10 to get k by itself. So k equals 1.5. And now I'm going to plug it in there because the second part of the equation says how many people, so now I'm going to be solving for people, would it take to assemble 36 machines in 8 hours? Well, let's see. 36 machines in 8 hours. So 8 hours, I work at a rate of 1.5. I want to do 36 machines, and I want to know how many people is that going to be. So I'm going to go ahead and multiply, all right, both sides. This is 54, so I get 8 equals 54 over P. Multiply both sides by P to get rid of it in the denominator. 8P equals 54, and then go ahead and divide it by 8. So 54 divided by 8 is 6.75. So 6 people, probably 7 people, right? Because we need to make up for that extra. So we definitely need 7 people.